Hello everyone. So this is going to be a video tutorial explaining the Ender Dragon behavior of Minecraft Bedrock Edition 1.21. So I wrote everything in this document, which I posted in Discord. I guess if you're watching this video, you can probably find it. But I kind of figured no one would really read it because no one reads. So I thought that I could make a video explaining all this, but a bit more simply and with some visual representation. So let's start right away. The first part, we're going to talk about behaviors. So as you can see, the dragon can have four different states. In reality, there are more, but we're gonna see those four ones because the others are a bit useless. So the first behavior is the fly behavior. In the code, it's actually called the holding pattern behavior, but that doesn't really matter. So to understand the fly state, you kind of have to understand the A star pathfinding algorithm, which I will explain later. But basically, how it works is that there are various nodes um, which are located in various places. For example, one node is here, right? Then there are other nodes. For example, there is one node um, here, right? And there will be one node at 28 here. And it's so symmetrical, right? There will be nodes like this in every direction. Um, so basically, the dragon will be able to only go to those nodes and switch direction there. I will talk further about those things later, so don't worry if you don't really understand. Um, so the second behavior is the strafe. Strafe happens when the dragon shoots a fireball at the player, and this happens only when two conditions are met. The first condition is that the the player must be within 64 blocks of the dragon, and the second is that it has to be plus minus 10 degrees angle from the point of view of the dragon. This means that basically you can think of the dragon as with a 30 FOV, but it's actually a 20 FOV, so it's like two-thirds of this. And the dragon will shoot a fireball only if the player is within the FOV. Okay, so to avoid getting shot by the dragon, you can try to um, not stay where it's looking towards, but stay a bit sideways, and that way it will never strafe. Of course, it's impossible to always stay sideways because the dragon constantly changes where it's looking at. But the further away you are from the fountain, the better it is. Or you could also just do this, right? This is a thing top runners do. And the dragon won't be able to strafe because it will actually have to see you. However, this has a problem, which is that when you're like this, the dragon can actually dive. So the diving behavior is the third behavior, and it happens when the dragon is less than 20 blocks away from the player, and it's regardless of whether the player is visible or not from the dragon. So if you are like here and you do this, the dragon won't strafe you, but if it goes to like the node at 20 0, which is here, okay, if it goes to this node, it will most likely dive anyways, um, which is obviously not good because diving is like the behavior when the dragon goes down and attacks the player. Sometimes it also strafes while diving, and after diving, the dragon has a 50% chance of diving again. However, if you test it or like have any experience with the dragon, you will see that actually the dragon uh, dives again less often than 50%. And I don't really know why, but I assume it's because sometimes after the dragon dives, it's actually like more than 20 blocks away from the player, and so it can't dive again for the previous conditions. It's probably because of that, but I'm not sure. And so yeah, this is the diving behavior, and this is the reason why you don't really want to block your shaft like this. It's a way, like if you're going for a very fast line or whatever. But it's actually better to stand like here. Okay, so well, of course, it's going to be the other direction because you spawn at posers. So yeah, the best way is to stand like here. So the dragon can't see you, so it can't strafe, and it will be able to dive at you only if it reaches this node. But if it does, you will be able to see it and you'll be able to go even further away, right? And then once it will be further, you can come back to the tower. The reason you want to come back to the tower is, of course, because if it's going to perch, then you'll have a very short time to reach the fountain, so you don't want to be 100 blocks away. Of course, if you have a pearl, you can just stand here and you will be safe. This is for 1.21. For 1.16, it's different. Okay. So yeah, don't worry me being a 1.16. It's for 1.21. So now let's talk about the perch. Actually, I'm not going to talk much about the perch because I kinda give it for granted that you know what perch is. So it's basically when the dragon reaches the perching node, which is the node where the dragon goes down to the fountain. And unlike Java, the dragon goes directly to the fountain and doesn't start circling, of course. Um, okay, so there are different types of perch, which I, of course, are completely arbitrary. Like I invented those names, but it's kind of nice to distinguish them. So spontaneous happens when like the dragon doesn't detect the player, and we'll actually see later how exactly that works in the code. 5RD is a bit weird. It happens on lower random distance. This is why it's called 5RD, but it can also happen as like at like 6RD too. And it happens. It's a bit weird because it like the dragon when it's going down, it dips its head on the ground and it perches very vertically. And it also goes very high before perching. So it's a bit weird. And then there is like the normal perch, which is the 9RD one, which is when the dragon just normally reaches the node and goes down. This is the standard one that happens in most ones. Okay, now let's talk about something a bit more advanced. So let's talk about nodes. So nodes. Okay, so let's start. Let's first talk about A star, which is the algorithm. So A star. Okay, you can read the definition from Wikipedia. I'm going to try to explain it a bit more simply. So basically, you can think of the dragon at any point in space. Okay, let's say it's here. This is not a node, but let's just imagine it is. It has various options of where to go. Okay, the nodes are the options. So there are points in space where the dragon can fly towards. To choose what node to go to, it will have a few variables, which will be a few factors. I'm sorry. So those factors will be um, the G factor, which will be the goal. The goal of course changes and it's actually one of the biggest questions, like what are the weight of the goals. I don't really know that, but like there can be various goals. So for example, the goal can be perching or it can be strafing or something like that. So there is the G factor and then there is the H factor. The H factor is a heuristic calculation of the no, I'm sorry, I completely switched it up. The H factor is the goal thing. The G factor is a calculation of the cost of reaching that node. So basically, it's how far away it is. And yeah, sorry, I switched it up. And then there's the F factor, which is the result of the addition of those two factor I previously mentioned. So the code does this calculation for every node, and the node with the best F factor will win, and the dragon will go towards that node. So I don't know if I was very clear, but you can read the definition from Wikipedia. So the nodes, therefore, are the connection points between the edges, and the edges are the path connecting the nodes. So nodes are just points in space. Okay, so if we look at the code, we'll be able to see that there are three concentric rings of node. which are respectively 20, 40, and 60 blocks away. And in the code, there's also variables for the angle steps of those nodes. So they are respectively 30 degrees, 45 degrees, and 90 degrees. And so, of course, having those information, we can calculate the exact coordinates of the nodes, which are those, if you care. Those are the outer rings. Now, those are pretty interesting because actually the Dragon never uses them normally in 1.21. In 1.16 it does, but in 1.21 it doesn't. So the Dragon never goes to the this far out, right? If you like have any experience, the Dragon never flies this far out, at 60 blocks away from 0, 0. But it actually does if you respawn it with the crystals like this. Right? If you do that thing, it will actually fly farther away. So I don't know really why they thought about doing this. My best guess is because technically the second fight will be harder, but like yeah, I don't know. So this is pretty interesting. So those nodes are basically useless unless you like care about the second fight. But they are useful for the 1.16 dragon actually, because the 1.16 dragon uses them also at the first fight. Then there are the middle range nodes. Those are useful because they are used in the actual first fight, and those are the nodes that are used most by the dragon. And they are all at 40 blocks away from 0, 0, so exactly what the towers are. Um, and the nodes there will be one 40 blocks away in each direction, and then there will be one at each diagonal direction at 20 blocks for both. So like here, right? In every direction. Okay. And then there is an inner ring with 4 nodes at the 4 cardinal direction, 20 blocks away from 0, 0. So those are the x and z coordinates. However, I haven't talked about the y level, which if you have some experience with the dragon, you'll see always changes a little. And the reason it changes a little, here is the like code. You don't really need this. This is the important part. You have to understand that IVAR 8 is the y coordinate, right? So if you check the code a bit after, IVAR 8 is added to a random value. The random value is FVAR22. FVAR22 is added, has a random offset, okay? Um, and this function will call a random function, all right? So there will be a random value times 20 times IVAR 8, which is the y coordinate, which basically means I assume that FVAR22 will be a value between 0 and like 1.5 or something, which will mean that the dragon will have also always a like 25 blocks range, completely random, in which it will fly at every node. And this is the reason why the Y level is always weird. Now, another thing a bit weird about the Y level is that the dragon, when it reaches those two nodes, right, the 40, 0 node and this other node, the minus 40, 0, it always goes a bit higher than on the others. And if you think about it, and by placing the blocks, I kind of made it evident. But like if you see the other nodes, they are all very near towers, but they're not on towers, right? Those nodes are on towers. And in the code, there's actually a function, which is these blocks also get above top solid blocks. This is a function, and basically it gets the top, like the highest, I'm sorry, the highest block in the node coordinate, and those two nodes will be the only ones that will be above towers. And so this is the reason why the dragon flies higher on those two nodes. So it actually has nothing to do with the perch. This is pretty interesting. And And so this function gets basically the base value of y, and so it will be basically either 8. All right. So I don't know if then either 8 actually has some addition to it. Like it probably isn't like just the base value, but that's like too hard to understand. But yeah, of course, this is the reason why the dragon goes higher on those shootouts and only those shootouts. All right, now let's talk about the matrix. This is very simple. Basically, the dragon can't go to every node once it reaches one. So let's say the dragon is at this node, at the node -28, -28. The dragon can't just go there, right? The dragon can't go this far. There is a matrix that determines what nodes can the dragon go to, but usually the dragon can only go to the closest node. So let's not consider the outer nodes because they are useless, as I explained previously. From this node, the dragon will be able to reach that node, and I believe the two inner nodes here and there. All right, so now I will show the visual representation of the matrix. Um, so this is the matrix. Yeah, so as you can see, I was standing here, and actually I picked the worst example possible because as you can see, the matrix is completely symmetrical except for this line. And I don't know really why. It could be because my decompiler is stupid, but it also could be like a bug in the code. But most likely it's actually an unintentional game design due to the fact that you don't want the dragon to always circle around. So maybe by removing one connection, once the dragon reaches this, it kind of adds more variation, if you understand what I mean. If you don't, it's fine, doesn't matter. And here are all the nodes. Those are the values here, right? So 0 has those coordinates and will be related to the number of nodes, and you can go fetch it right earlier. And yeah, but it's pretty simple and it's a bit obvious, so this is a bit redundant, but just in case I put everything. Yeah, so those are, as you can see, it's actually very simple. So now let's talk about the spawn and the first nodes. So this is actually the kind of the hardest part because it's not very clear. This is actually very hard. So the dragon spawns at the coordinates 0, 128, 0. So the dragon spawns here every time. So it's very high, and it always goes down, obviously. And the way it chooses the first node is very weird. So basically, um, it depends on various things. First, it depends on the seed. So this function is actually seed dependent. So on the same seed, the dragon will always choose the same node. But this is not actually completely so, because to different people, the dragon chooses different nodes. So and also on different random distances, the dragon chooses different nodes. So it's weird, right? And the reason for that, uh, I don't know, to be honest. But there are a few possibilities. So at the end, I explained a theory, which is that this value, which is an offset, is never initialized, so it's garbage. Garbage just means that it's like never initialized in the code. It's a it's a programming concept. It's not garbage in the sense that it's like bad, uh, although it also kind of is. But basically the base concept is that this value is random, but like not really, in the sense that if it's low, this will mean that the dragon will have very few, um, will behave the same way multiple times. And if this value is high, then it will mean that the dragon will change a lot its behavior. And this actually is completely speculative, but it kind of makes sense because if you test it, the dragon very often does the same behavior multiple times, which is a bit weird considering all the possibility it has. But yeah, of course, this is totally speculative, so I don't know. But yeah, the base fact, which is for sure, is that it's based on seed, and then it's also based on random distance, which, as you can see here, this is in italics, so it's speculative, but it's probably because newly loaded chunks uh, probably have some sort of weird stuff going on, um, which would also explain the 5RD perch thing. Yeah, another thing about the 5RD perch thing. So let's say the dragon goes here and it wants to perch, right? Or it also doesn't want to perch, it doesn't matter. So technically the node will be like here. It will be here probably, or like even higher. But the dragon will not go this high, right? Usually when the dragon goes to this node, it will go like to 105, but it won't go to the actual node. The reason for this is because uh, z and x value have priority over y value, which means that once the z and x coordinates are reached, regardless of the y coordinates, the dragon will still choose a new node. So it won't like fly up until it reaches the actual point. So this is very important. And on the 5RD perch, the dragon actually goes higher, which means that it stays more time on this node, which probably means that because the chunk is freshly loaded, the dragon goes higher, and which also explains why it then is more vertical and it goes very low on the fountain. All right. Of course, this is speculative, but it's the best explanation I could give. And yeah, about the hardware dependency. So the fact that to different people and to different machines, the dragon behaves differently. I, to be honest, have no clue. It could be because of the uninitialized memory, but it could also be other things. To be honest, I really wasn't able to understand this. This is probably the biggest question that I wasn't able to answer. Okay, now let's finally talk. This is the last topic about the purge. So how does it work exactly? So there are two types of purge actually. So before I told about three types, actually the 5RD and 9RD have no difference in the code. But the spontaneous one and the other two ones have actual differences in the code. So let's look about them. So at the start, all right, the purge location is set at the center fountain, which in the code is called podium, which is at 0, 0, and the y level is based on the get above top solid block function, which is the function we saw earlier and is the function that is responsible for the dragon going higher at those two nodes of the towers. So it's the same function, however, it's for the podium. So this means actually that, for example, if I place um, blocks like this, actually the dragon will perch much higher, right? Because the function get above top solid blocks will give 84 in this case. And this also means that if you do something like this, the dragon will perch at 24-0. But of course, to do that, you will have to find a way to break Bedrock, which is not very easy. Okay, so then there will be a function which is fetch nearest attackable player. And this function will search for a player within 150 blocks from 0, 0. All right, there will be a 150 blocks radius. And if a player is found within this radius, it will just get his coordinates. If not, never mind, it will output that there is no player. However, and this is not in the code actually, or at least I didn't find it, but like empirical testing found that if you shift at further away than 102 blocks from 0, 0, the driver still won't detect you. So this function will still return that no player is detected. And finally, of course, if you are in creative, no player will be detected. All right. So if this function returns that there is no player, this code will be calculated, will be used. So basically what this says is that the z value of the perch target will be 0 and the x value will be 40. Now let's try to understand what this means. What is a perch trigger? So this means basically that the perch trigger will be at this coordinate, right? So this is what the player spawn, to be clear. This is the obsidian thing. So this is east. So when no player is found, the dragon always perches east. This is something that is obvious. It's the reverse perch logic, right? But if you think about it, most of the time the reverse perch doesn't happen at 40-0, but it happens at 20-0, right? The dragon reaches this node and perches. So why that is? Why I said 40-0, but the dragon perches earlier or sometimes farther away or whatever? Well, the reason for that is that the target node doesn't necessarily mean it's the actual perching node. So actually, what is really important to understand is that there is a versor. A versor is just a vector with no length, right? So it's just you can imagine it as an infinite line. Actually, the versor has unit one, like length one unit, but it doesn't matter. You can think of it like an infinite line. So whenever the dragon will reach this line, it will always perch. So I'll give you a practical example. Let's say the dragon spawns here, right? It will decide to go as a first node here. Then it won't detect player, and it will try to go perching. So to go perching, it will go to this node first, to minus 20 node, and then it will go to yeah, I'm sorry, I have my directions wrong. I meant to say that the dragon went this way first, yes, then this way, okay, and then it goes this way. Okay, now it reaches the vessel, so the dragon perches immediately. It doesn't first go to the target node and then perches. So I hope this was clear. I also explained it in the document. I explained it in this section, so if I wasn't clear, you can read this and maybe it will be clear. Now let's see what if the player is found. So it will give the coordinates of the player. The y value is ignored. So what happens is that the game builds a vector. So this will have a distance from the center to the player. All right. Then it will normalize it, which means it will return a unit vector, which is a versor, which means that it will basically remove the distance value. Okay, so it will not matter whether the player is standing here or 100 blocks away. It will always return the same value. All right, and then it will multiply it by minus 40. What does this mean? Well, this means that if you put a minus on a versor or a vector, it will just return the opposite white line. And this explains why the dragon always perches at the opposite direction for the player. And 40 is again the target node. So the target node is always on the middle ring, but this does not necessarily mean that the dragon will always perch at the middle ring. This is very important. All right. So yeah, this is basically it. I will talk about this last thing, which is um, basically there's a slight delay on when the dragon decides to perch. So the dragon decides to perch a bit with a slight delay because the dragon tries to search for a player every tick until it's within 10 blocks of its target node. So the node returned by the A star algorithm function. So whenever it's like within 10 blocks of the node, it will stop searching for the player. And now, yeah, this is it basically. I will just say that according to empirical analysis, it does appear that the dragon decides the next target goal 10 blocks before reaching the actual previous node, which means on basically giving an example, let's say the example of before. So the dragon spawns at 0, 0, goes to this node first, then decides to go to this node because it's the closest to the perching node, because the dragon decided to perch, because yeah, that's his goal. And then the dragon goes here, right? Um, so basically the perching decision happened like here, right? When it reaches the previous node to the perching one. This is my theory, and it will kind of explain why, for example, if you do the reverse perching thing, right? So when you spawn, you throw a pearl and you shift at at x 102. The dragon, even after the pearl lands, he isn't already perching. Is almost perching, but it's not perched yet. And although it could see the player, it doesn't, and perches anyways all the time. And this could be explained only with my theory. So yeah, this is not the code though, so it can't be 100% confirmed. I mean, the 10 blocks thing is in the code, but it doesn't really explain whether the dragon decides to perch. So yeah, this was it. Yeah, I'm not going to explain the other theories because they are a bit too technical, but if you want, you can read them on the PDF. And yeah, finally, let's talk about what I didn't understand. I already kind of mentioned everything, but I don't really know how the dragon chooses its first node. I know it's seed dependent based on the get random function, but I don't know why exactly it's based on the machine. And I also don't really know why it's based on random distance, although for that at least I have a theory. Um, yeah, then okay, this is basically the other theories part, which is obviously completely speculative. So yeah, I don't know. But it's basically based on the memory allocation problem. So the garbage thing I talked about earlier, like the fact that those values are never initialized. Those values are the ones we saw earlier. Yeah, I kind of forgot what they were, but it doesn't matter. You know what I'm talking about. I talked about it earlier. Then the goal weight. So basically, the dragon has a lot of goals, which could be strafing the player, perching, etc. But I actually don't know the weight of these goals. So I don't know, for example, if the dragon prefers to perch or dive or strafe. And of course, this is key to understand the actual dragon behavior, because if I don't understand what the dragon prefers to do, I don't know, of course, what the dragon will do more often. Of course, this can be understood with empirical analysis. For example, it's pretty clear that in 1.21, the dragon prefers to perch a lot more than most other things. Um, for example, in 1.16, it's sure that the weight of the perch will be much lower. And yeah, and finally, there's this little thing of the dragon sometimes not perching when it reaches the target node. So let's say I'm standing at like here, okay? I'm standing here and I'm waiting for the dragon to perch. The dragon goes here, it goes high, it seems like it's perching, it goes here, and instead of perching, it strafes. It sends a fireball and keeps flying. This happens pretty rarely, but it happens. So yeah, it's a bit weird, and I have no clue why it happens. Yeah. And finally, there is one more thing that I didn't even mention in the PDF, but it's very weird. So there is one perch that very rarely happens, where the dragon just perches immediately at the first node, although it's not on the opposite node of the player. This is so weird. I have never understood it. But yeah, this is another thing um, that very rarely happens, and I haven't found any explanation of it. So yeah, I hope this video taught you something new. And of course, all this information will have practical value. And I already figured out a few ways of um, using and manipulating dragon disinformation to affect the dragon behavior. And later on, I will probably publish other videos. I already published a few, but they are unlisted. Later on, I will publish better ones publicly, so that you will see some practical implications of all this mess I explained right now. So if you care about the having this PDF, you can join the Discord. I will put it on the description. And yeah, thank you for watching this video.